Good afternoon. I am Mr. Ish. Thank you for watching. Thank you for liking. We are doing here a good, interesting video over here, slightly out of the ordinary. We're going to define the area of a circle using a pair of parallel lines, a transversal line, and the angle that's generated by means of that transversal line. What does all of that mean? If you draw a pair of parallel lines and you cut it by a transversal line, you know you generate a certain angle. You can represent that as an x, or you can even utilize this right here if you want, the theta. If you were to squeeze in a circle between these two parallel lines such that they would be tangent, you could very well do something like this. It's tangent here, it's tangent here, here's your center of the circle. You know, by means of a very important geometric theorem, a tangent is always perpendicular to the circle at a line and at a point which connects it to the radius. This right here must be 90 degrees. If you draw another tangent line, it doesn't matter what direction, so long as the tangent line is on a point which connects to the radius, is always in 90 degrees. That right there is a theorem, a very important geometric theorem. If you have this representation which I've drawn for you, you know very well that this right here is going to be 90 degrees and this right here is going to be 90 degrees. A good way to draw the circle would be exactly this. What does all of this mean in terms of the pair of parallel lines, a transversal line and that? We can very well determine the area of this, or we can classify or define the area of that circle utilizing that description we have over here. Everything I've shown you over here can very well be drawn on an XY plane, and you don't have to do it for this. I'm just showing you everything here can very well be mapped out. You can get out all of these points in terms of coordinates. You can do all of that. But that right there is besides the point, but it shows you the very important fact that whatever I'm showing you over here can very well be done on an XY coordinate plane. It wouldn't make any sense that this right here, from this point to right here, if you squeezed in a circle, that it would represent a diameter of your circle. By no means would that be correct. This right here would not be a diameter because it would be incorrect depiction. It wouldn't be tangent in the sense right over here because you have a lift over here going on. You wouldn't have a true point over here because the circle would have lifted away from your parallel lines. Don't go and confuse yourself with this as being a representation of your diameter, that this right here represents your diameter. It by no means is, because it wouldn't have that 90-degree relationship of the radius with that parallel line or the tangent line. Here the parallel lines are tangent to the circle. The only way you can get a good effect here in terms of the circle fitting in with regards to a representation of the diameter, here is your transversal line, is by means of this. You consider this as one of your points tangent to the circle and you draw a circle like this. Now very well you have what appears to be a good representation of a line, parallel line, which is tangent to the circle. Here's a parallel line tangent to the circle. If you draw a 90-degree line or a line perpendicular or connecting these two dots, you by all means have fulfilled a line which is a diameter line and it's perpendicular to both of your parallel lines. So this transversal line does not really fit very well in terms of a diameter, but again we have to utilize the transversal line and the parallel lines to get the area of this circle. So how can we do it? I've shown you that this is how you would look at it, and everything here can be drawn with respect to an XY coordinate system. Just keep the circle right out of here, out of the picture, out of the way, and look at this accurate depiction you have over here and very well draw a line down here and create a 90-degree and create a right triangle. You have what happens to be right here. This segment right here is D. We can call that D for a diameter because it very well approximates the diameter of this circle. This circle diameter approximates that segment or the side of that triangle. Call this H for hypotenuse. If you were to know the dimension of this H, and you could, if you drew everything on a Cartesian coordinate system, you could get the distance of the segment. You very well can, and you can always utilize the angle to determine this diameter. Let's blow everything up over here with regards to our triangle. We have what happens to be here, my transversal line, and angle created by that. I have a H over here, I have a D over here, I have a 90 degrees. If this right here is a theta angle or an X angle, the opposite angle must also be the same. This right here is 90 degrees, that's 90 degrees. So this right here must be 90 minus theta. These two angles here would be complementary. If one is theta, the other one is 90 minus theta. You can use the definition of cosine to very well get the dimension of D. Cosine 90 minus theta is equal to D over H. With regards to this angle here, D is your adjacent, H is your hypotenuse. Then D, which is here the side you're looking at, which at the same time also represents the diameter. We can say d here is equal to the diameter. By coincidence, it happens to be the diameter of your circle. It will be equal to h cosine 90 minus theta. Clean this up over here using the cofunction identity. You know, sine theta is equal to cosine 90 minus theta. The sine of an angle is always equal to cosine of its complement. Likewise, cosine theta is equal to sine 90 minus theta. You can use this cofunction identity. I have a cosine 90 minus theta, so all of this is equivalent to h sine theta. Alright, this right here is very well equivalent to this. So we've determined the diameter. The diameter is equal to the hypotenuse, this segment, times sine of theta. And you know diameter is always equal to twice the radius. Radius is equal to d over 2, right? Half the diameter is your radius. And then this right here would very well equal to h sine theta over 2. And this right here would be your radius, and we've determined the radius. Now to define the area of the circle, it's easy. We know area is equal to pi r square, and we have the radius. And we can finish this concept question very quickly. Area is equal to pi r square, which is pi, and then we have h sine theta over 2 square, which is equal to pi h square over 4 sine square theta. And this right here would be equal to area of your circle, which is tangent and in between two parallel lines and defined with regards to an angle that's created by means of a transversal line. And that right there is it. This right here would be a very good formula for this specific depiction we have drawn over here. Again, remember, you could not draw a circle over here in such a way and expect this diagonal line to serve as your diameter. It by no means would be your diameter, because in that instance, these parallel lines would not be truly tangential to your circle, because they wouldn't have a 90-degree relationship with regards to the radius that would connect with it. It just wouldn't connect with the radius, and you wouldn't have the 90 degrees. The only way you can squeeze in a circle right here is right exactly in this manner right over here. Of course, my drawing is a little bad over here, but you can see how it is. And the transversal line by no means depicts a true and accurate chord, which is your diameter. It depicts some form of a chord, but it is by no means a diameter chord. Anyhow, by drawing a perpendicular line, you develop that diameter. This transversal line and its angle then come into play by means of the procedure I've shown you over here. Defining the circle area using parallel lines on a transversal line and the angle will lead you to this formula right here. Pi h square over 4 times sine square theta would very well give you the area of the circle. You would just need to know what this h segment is, this segment right over here. That segment can very well be determined from a Cartesian coordinate system. You'd have some x comma y point here, you'd have another x comma y point here, and you could easily determine the segment using the distance formula from coordinate geometry. And with that, I thank you for watching this video. Have a good day. Bye.